Hi guys, in this video tutorial I'm going to show you guys how to create a calibration curve from your standard measurements, and this is going to be useful for a lot of the labs you're going to do in the future as well as assignment 2. So to start off, here we have a dataset that I downloaded from Avenue. We have all our different standards, their concentrations, and the absorbance values measured in triplicates. And the first thing we're going to do is calculate the average of our blank, and do that, we just type in the function average and select our blank measurements. And now we're going to subtract all of our absorbance values from this blank measurement. So this is going to be corrected absorbance and equal sign. I'm going to select the absorbance value and subtract it from the average. And because we're going to be doing this for all the cells, and we're going to keep the red cell constant, we're going to type in the $sign between that cell, hit enter, and if we hold Control or Command for Mac and drag down, we've corrected all our values. So now we have a corrected measurements, but we need to calculate the average of each measurement. And before we do that, I'm going to translate this data from triplicates to singlets. So let's do the same thing here. Here is going to be average corrected absorbance, and we're also going to calculate the standard deviation over absorbance. So standard corrected absorbance. Okay. So to do that, I'm going to use the average function, this here, and then if we drag this all the way down, you'll notice that it hasn't picked the right cells, so we'll just have to adjust that by moving this box around. For our standard deviation, and we're just going to use the standard deviation function in Excel to do that. So we have our average and standard deviation for all our measurements, and now we're ready to create our calibration curve. So we're going to highlight our concentration and our absorbance values. We're going to go to Insert and select the scatter plot and just throw that in. So Excel doesn't have the prettiest default sort of design for these graphs, and you can choose to change this however you want, but I'll show you guys a pretty good way to make your graphs look nice. I like to remove the grid lines from a graph, change everything to black instead of gray, and remove pretty much all color. And change this to, choose the marker here. I don't want a border, and the fill is just going to be black. And we want to have major tick marks inside, so we'll go to tick marks, major type inside, and also you could see that there's a lot of excess space here, so we can rescale our X and Y axes. So the maximum value here is 2000, so I'm going to change that to 2000 and change this to 1.2. Oops, keep that at 1.4 actually. And also have the tick marks be inside here. And the minimum value, we can just keep it as 0, even though some of the values are slightly negative. Then I'm going to also remove the fill that the actual graph itself has, and we finally have a decent looking graph. You want to add a title to your calibration curve, and I'm just going to put BSA calibration curve and change that to black as well. Okay, so now we have our points, but there's some sort of error associated with all these points. So if we go to our data here, we go to design, add chart element, error bars, and we'll just click on standard error for now. And if we actually go to our error bars and go to the data, instead of standard error, change it to custom, and we're going to select the standard deviation values for both the positive and negative error. So this is our positive, this is our negative, and voila. We don't need error bars for the X value because there's no error associated with it. I'm going to make this slightly thicker. So if we go to align, I'm going to make it 1.25. Okay, great. So now we have our graph somewhat pleasurable to the eyes to look at. There we go. Okay, and oh, one final thing. I don't like this border. Okay, finally. So here's our graph, and now we want to determine a line of best fit for the linear portion of the data. To start with, I'm just going to select our entire data, and we'll worry about the linear portions later. And to do that, we're going to use the lines function to calculate the slope and a bunch of other important parameters from our line of best fit. So we're going to select one cell, type in the function linest, select all of our y's, comma, all of our x's, and set the two other parameters for true. We hit enter. Now this is just a slope, but there's a bunch of other information that we can gather. So I'm going to select the cell and a 3x2 selection around it. And if I click on the formula and hold Control and Shift and hit enter, we get a bunch of other values here. Okay, so this is our slope. This is the error associated with our slope. This is the R squared value, which describes how good our fit is. And here is our y-intercept, the error associated with the y-intercept, and some error associated with y as well. Okay, and these values are important for the future, where we're going to calculate the error, the interpolation error that we're going to use to calculate our unknown. Okay, so now that we have the slope of our line of best fit and the y-intercept, we can actually draw the line of best fit onto our graph. And the way that I'm going to do that is I'm just going to plot two invisible points. So here's our line of best fit, and x and y. We can set it as 0, and also our maximum value, which is 2000. Okay. And now we have to calculate y, and we just use the y equals mx plus b equation. So select x, multiply it by the slope, which we will again keep as a constant cell, and add our y-intercept. Oops, there we go, and drag that downwards. Okay, so now we can plot our line of best fit. I'm going to right-click on the graph, click on select data, add another series. This is going to be a line of best fit series. The x values are just 0 and 2000. And select our y values. We hit enter. Okay, and now we have our 2 points, and there's something wrong here. Let's see. Oh, forgot to make this cell constant. Okay, drag that down, and now this should have readjusted. And there's something wrong with our line list function here. Oh, and that's because I did not choose our corrected absorbance values. So I'm just going to go back here and correct for that. There we go. This makes a lot more sense now. Okay. So I'm going to select my calibration line of best fit dot here, and I'm going to make it appear as invisible. So no fill and no line. And if we go to line and put solid line, we get our line of best fit right there. I'm going to make that a little bit thinner. Okay, and perhaps we can change this to 1.6. There we go. Okay, but we could see that it's not really representative of our data. The linear portion seems to be lying just in this area over here, disregarding the last 2 points. So we're going to go back to our line list function and deselect the last 2 standards, and again hit Control-Shift-Enter. And we could see that our line of best fit automatically adjusted, but this sort of seems that implies that we can extrapolate our data, so I'm going to change the x value here to 1000, and now we have our calibration curve. We of course need to add some axes titles, so go to add chart element, add axis titles, primary horizontal and primary vertical. This is our corrected absorbance arbitrary units, and this is our BSA concentration in micromolar. You should use the actual microsign instead. Change that to black as well. Okay, cool. Now what you want to do is, say we have an unknown value of around, so you guys measured your unknown and you got 3 different values. You got 0.675, 0.683, and 0.671. And to get your concentration, you need to interpolate using the line of best fit from Y to X. So first we're going to calculate the average value of signal. And so this is going to be measurement 1, 2, and 3. This is the average. And now we have to get our X value, or concentration. And we use the y equals mx plus b equation. So this is our y value. So we can subtract the y-intercept from that and divide it by the slope. So our unknown is going to have a concentration of about 650 micromolar, but we need to calculate the error associated with this measurement. And we're going to use this very pretty looking equation on the right here, which is actually in your notes. So let's dissect this equation a little bit. First, we have the uncertainty in the y value of our calibration curve, which we get from here. We have the slope of our calibration curve. And then we have k being the number of replicates, which is 3. The number of calibrants that we have is the ones that we use to create the linear calibration curve, and that's going to be 1, 2, 3, 4, 5, 6, so 6 values. And this term here we can calculate by subtracting our average y measurement from the average y of the entire calibration curve. And this bottom value here we can calculate using a specific Excel function called dev square. So we'll calculate each of these terms and then combine them all into one formula. So first I'm going to calculate, I'm going to have k here as 3, n as 6, we already have sy and m. This top term here is going to be calculated with this formula. So take our average y, subtract it from all of these up until this point, and we're going to square this entire term here. Okay, and the second value we can calculate using dev square, and that's going to be all of this right here. Okay, so now we can calculate Sx, and so we have Sy divided by our slope, multiply that and use a square root function, 1 over k plus 1 over n plus this divided by that, and multiply this by the slope squared. I avoided using the brackets here, so I divided twice, and close that. And so here's our error value. So we can report our concentration as 650 plus minus 30. Okay? Another thing that you guys need to do is insert the equation for the line of best fit. So to do that, I just go to design, format, and I insert a text box right down here, and use the equation tool to insert the equation. So y equals mx plus b. Well, we also have to include the error associated with m and b. So m is going to be 0.001, going to be plus minus 0.00002. And so we can add a few more values here. 0, 6. So here we have 5 zeros until our first significant digit for our error, and here we have 6 significant figures before our last value here, and put an X. And our y value is going to be 0.009 plus minus 0.03, or rather 4. So we can scale this down to 1. All right, great. close that. And stretch that out a little bit. And there we have it. Okay. Now you can also calculate your limit of detection and also your limit of quality, I believe. And to do that, we have the error associated with our blank, and the limit of detection, or LOD, and here we have the LOQ, is 3 or 10 times the standard deviation of our error. So, and we have to interpolate that value back to the X value. So we'll first get the Y value of the limit of detection, and that's just going to be 3 times our error for our blank, and it's going to be 10 times that. And we use the y equals of x plus b equation. What did I do? Over here. And when you're reporting your values, make sure you're using the same units as the ones that you had in your calibration curve. All right.